The world of generative adversarial networks, GANs. A journey into AI creativity. Introduction. Welcome to the world of generative adversarial networks, GANs. A journey into AI creativity. In this audiobook, we will explore one of the most groundbreaking innovations in artificial intelligence, generative adversarial networks, or GANs. From their origins to their applications, and the hardware needed to run them efficiently, we will dive deep into the realm of AI-generated creativity. The history of GANs. The story of GANs begins in 2014, when Ian Goodfellow and his colleagues introduced the concept in a landmark paper. The idea was revolutionary: an AI framework consisting of two neural networks, a generator and a discriminator, competing against each other in a zero-sum game. This adversarial process enabled machines to generate incredibly realistic data, from images and music to text and beyond. Since then, GANs have rapidly evolved, influencing numerous fields and inspiring researchers worldwide. Understanding GANs. At its core, a GAN consists of two key components: the generator, which creates new data samples by learning patterns from existing datasets; the discriminator, which evaluates the generated samples and determines whether they are real or fake. Through an iterative learning process, the generator continuously improves, producing increasingly realistic outputs. This dynamic interplay has made GANs one of the most exciting AI architectures today. GANs are typically implemented using deep learning frameworks like TensorFlow and Keras. Keras simplifies the process of building and training GANs with its intuitive API. A well-structured GAN uses components such as batch normalization to stabilize training by normalizing activations, reducing internal covariate shifts. Deconvolutional layers, transposed convolutions, are crucial for upsampling in the generator to create high-resolution images. Interpreting the loss of the generator and discriminator is key to understanding GAN training dynamics. The generator aims to minimize the discriminator's ability to differentiate real from fake data, while the discriminator tries to maximize this ability. Ideally, the discriminator's loss should hover around 50% accuracy, indicating balanced competition. A continuously decreasing generator loss suggests that it is learning, but mode collapse, where the generator produces limited variations, must be addressed. Common problems in GAN training include instability, mode collapse, and vanishing gradients. WGAN, which utilizes the Wasserstein loss function, addresses these issues by using the Earth mover's distance, leading to smoother and more stable training. Other techniques to improve training include adding gradient penalty, tuning the learning rate, and employing spectral normalization. The recommended number of layers in a GAN depends on the complexity of the task. GANs, for instance, use a deep architecture with multiple convolutional layers, while simpler tasks may require fewer layers. Generally, GANs benefit from a balance between depth and computational efficiency, avoiding excessive complexity that could lead to training difficulties. Popular GAN architectures. Over time, several powerful GAN variants have emerged, each with its unique capabilities. Deep Convolutional GAN, DGAN, introduces convolutional layers for better feature extraction and image generation. Progressive Growing GAN, TGAN, generates high-resolution images by progressively increasing the complexity of the network. Style GAN, developed by NVIDIA, enables fine-grained control over image attributes, producing highly realistic faces. Big GAN is designed for large-scale image generation, improving diversity and quality by utilizing massive datasets and computational power. Cycle GAN is a specialized GAN used for image-to-image translation, such as transforming paintings into photographs. Wasserstein GAN, WGAN, addresses training instability and mode collapse issues by using the Wasserstein distance metric, allowing for smoother and more stable training compared to traditional GANs. These architectures have revolutionized various industries, from entertainment and art to healthcare and fashion. Applications of GANs. The impact of GANs extends far beyond research labs. Here are some prominent real-world applications. Art and creativity. GANs can generate paintings, music, and even poetry, pushing the boundaries of human creativity. Deepfake technology. While controversial, GANs are used to create hyper-realistic synthetic videos, often for entertainment and media. Medical imaging. GANs help in generating synthetic medical scans to aid in diagnosis and training AI models. Gaming and animation. Game developers use GANs to create realistic textures, characters, and environments. Data augmentation. GANs generate synthetic datasets to enhance AI model training when real data is limited. Drug discovery. GANs assist in the creation of new molecular structures, accelerating pharmaceutical research and development. These applications demonstrate the versatility and transformative power of GANs across multiple domains. Hardware and storage requirements. Running GANs efficiently requires robust hardware. Since training a GAN involves heavy computations, the following components are essential: GPU power, High-performance GPUs, such as NVIDIA's RTX and A100 series, accelerate training significantly. Memory: at least 16 GB of RAM is recommended, but 32 GB or more is ideal for handling large models. Storage: datasets for training GANs can be enormous, requiring SSDs or even dedicated cloud storage solutions. Cloud computing: services like Google Cloud, AWS, and Microsoft Azure provide scalable GPU resources for training complex GANs. For hobbyists and researchers, cloud-based GPU solutions offer a cost-effective alternative to expensive hardware investments. Conclusion: generative adversarial networks have transformed the AI landscape, unlocking new possibilities in art, science, and industry. From their inception to their widespread applications, GANs continue to push the boundaries of what machines can create. As research progresses, the future of GANs holds even greater potential, shaping a world where AI-generated content becomes indistinguishable from reality. Thank you for joining us on this journey through the fascinating world of GANs. Stay curious, keep exploring, and let the power of AI creativity inspire you.